Hello everyone and welcome to the next webinar series. I am Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. We are eager to learn all about our today's webinar titled Application of Fiber Reinforced Polymer Composite Solutions to Geotechnical Engineering. A PDF of this presentation can be found in the handout box. You can use the PDF to follow the presentation and take notes if you desire. You may use the question box to ask questions during the webinar, and a speaker will be happy to address them at the end of the presentation. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion of 1 PDH. Your certificate will be available in ACI University under the Certificates tab within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of our disclaimer on the screen for next webinar series. Let's get started with a short description of our today's webinar. Today's webinar will discuss the use of FRP in ground engineering applications such as rock anchors, soil nails, and rock bolts. It will focus on how these composites are now utilized in permanent geotechnical engineering projects like tunnels and slope stabilization due to well-established long-term behavior studies. Let's explore today the evolution of these systems and their varied applications. Our learning objectives for this webinar are as shown on the screen. Let's welcome and introduce our today's speaker, Mr. Pierre Hoffman. Mr. Hoffman holds a Master's of Engineering from École Centrale de Lille and a Master's of Science in Project Management from Eskima Business School. He joined Dextra in 2007 with a mission to develop innovative solutions using composite material in power and transportation market segments. Since 2016, Pierre oversees the geotechnical product line, promoting fiber-reinforced polymer systems to be used in concrete and underground structures. Let's welcome Mr. Pierre Hoffman and listen to his presentation.
Thank you very much, and pleasure to be with you this morning. Good morning, everyone. Thanks to Next and ACI for this opportunity. Without further delay, let me start reviewing the content for today. So the idea is today to propose a slightly different angle from probably other presentation that would be focusing on FRP rebars. Many FRP rebar manufacturer member of the NEX, and at Dextra we also wanted to present a slightly different angle, which is through geotechnical engineering. So we'll start with introduction and properties that would be relatively common to the material, which in many cases is the same as the rebar, but we will explore the different fields of application, again specific to geotechnical engineering, reviewing the reference standards that again we share with rebars, and then we'll dive into 3 specific example or type of application, which will be slope stabilizations, deep excavations, and tunnels and caverns. So starting with the introduction and the properties, as I hope many of you know already, FRP stands for fiber reinforced polymer. Very often the P is mistaken for plastics, which is reductive and in many cases not correct. Why? Today I would say the vast majority of FRP are produced with a type of polymer that is not a thermoplastic, but rather thermoset resin. So you have example here, a non-exhaustive list of resin. And of course, the main component of the product is the fiber. Again, here, a non-exhaustive list of fiber, but those fiber and resin are the one we're gonna explore today, at least partially. So today's presentation will be vastly focused on glass fiber, so GFRP product, which remain the most common product. I'll touch base a little bit about carbon fiber, and also we'll explore the different resin with different applications. So again, similar to what is done for rebar, polyester is exclusively used in temporary application, and for most codes, temporary definition is less than 2 years, while vinyl ester and epoxy are resin that are suitable for permanent application. And we will see how this can be used as well in geotechnical engineering. Few properties, again, about the material. One thing that has been largely used for in geotechnical engineering is the cuttability. So the characteristic of the material that is easy to break down, destroy. It might sound surprising when you think about construction, but actually this material has been used a lot for that, starting with soft tie application in TBM tunneling. So this is where we had the crossroad between concrete reinforcements, because it's used in diaphragm wall, and on the same time it's used for tunneling purpose. So this is a typical property that has been used a lot, and you will see again how we can use that in today's presentation. As we know, those materials are extremely light, a quarter of the weight of steel. For GFRP, it's even a fifth for carbon fiber reinforced polymer. It's of course very much used when installation has to be done in complex area, especially in slopes where crane are difficult to have access, or even underground where you are working at a phase that can be several kilometers away from the entrance of the tunnel. Again, the material is greater than steel in tensile properties. We'll see that. It's also corrosion resistant. We'll also tackle that aspect. And there are some other characteristics that could be interesting in niche applications, such as the fact that it's electrically non-conductive, thermally non-conductive, also transparent to magnetic fields. Let's dive now into something that, again, is really the specifics of geotechnical engineering. The fields of application we're going to see throughout the cases today. We will make differences between what we call active anchors and passive anchors. So I just wanted to give you a little bit of introduction around that. The main difference between those two type of anchors are primarily the type of structure where they're installed and also how they are used. Generally, those products are relatively similar, but the main difference is an active anchor is tensioned at installation stage, and that's to reduce the movement before the product is mobilized and therefore can produce its effect. So the typical places where you get active anchors are in retaining structure, retaining wall like diaphragm wall or board pile, again to minimize the movement of the structure. And so it generates additional effects such as creep or fatigue and relaxation, while passive anchor are unstressed product, again, so that would be similar to a passive rebar. And again, why in those applications like slopes, it's possible to have the ground to move several millimeters or sometimes even centimeters before the product actually contributes and holds the soil in place. So just wanted to have a quick, let's say, definition or introduction here, because you will see that will have impact on the key parameter that we are studying through this presentation. So looking at the fields of application, what I propose today is to explore several properties of the material, of the product, through the specific purposes, so through the specific application we are studying. So after introducing the difference between passive anchor and active anchor, another key aspect is the duration the product is used for. So As mentioned in the first slide with the resin, we also differentiate in geotechnical application what is a temporary anchor and a permanent anchor. Whether you look at European codes or recommendation in North America like PTI, there's always a difference that the threshold is 2 years. So a temporary anchor will be less than 2 years, a permanent anchor will be more than 2 years. And so looking at this, we're going to explore several examples of products and the associated properties. One thing that is common to all these products, we will be exploring all kind of anchors at large, again, also soil or rock anchors, rock bolts, active anchors, or tiebacks. All these are grotted products, grotted anchors, and therefore the tensile properties remain the main dimensioning aspect, and of course bonding, not with concrete, but in this case with grout, are key aspects. So we're going to study that first. After that, we're going to see parameters that are key in different applications. So for passive anchor, we're going to study shear strength, which is generally a key concern of the designers. We're also going to review creep rupture, which is an issue or can be a concern for active anchor, and see how we address that when designing such structure. And as far as permanent anchors are concerned, we're going to review long-term characteristic of durability and alkali resistance to ensure the product is suitable for long-term application. Again, before diving into the actual example, I wanted to highlight that in many cases, geotechnical guidelines are strictly talking and addressing steel anchors, steel products. There are very few exceptions to that. So the vast majority of projects we design with non-metallic anchors, we are using the design philosophy of those geotechnical guides, but we do have to refer very regularly to specification codes that have been purposely made for FRP. And in that context, ACI, since the first version of ACI 440.1, and of course the associated ASTM standards are widely used. So we are very often using key design parameter or part of specification of ACI and applying them into geotechnical guide when it comes to design. So again, similarly to rebar, where we want the consistency between material specification and design code, we are really trying to keep this unity of consistency between ASTM D7957, ACI 440.1, or more recently 4.11, to ensure our design have addressed the specificities of FRP material. So as I highlighted, the first aspect of the rebar would be tensile properties and bonding. So as far as bonding is concerned, just wanted to illustrate that when we are looking at an anchor that is grouted, we do care for good bonding properties with cement grout. That could be with resin grout as well. So typically, one way FRP bars can transfer the load to the surrounding material are through surface deformation or enhancement. So a typical geometry used is to have sand coating and or helical wrap. And that's why actually we can ensure we exceed the requirement of ASTM 7957 as far as bond strength is concerned. That's also these kind of properties will be great help when it comes to designing ground anchor. So here you have example of actual result obtained with this kind of bars. I repeat, such bond properties will be essential to a good product. Of course, when it comes to tensile, similarly to what is done in rebar, I would say the industry has quite well addressed and educated the market on the properties. But maybe for some of you who might not be so familiar, the specificity of FRP bars are we always need to test them in full section of bars. We cannot characterize a coupon sample of the material because the properties are not linear with the section. There's a phenomenon called shear lag, which means the properties will not remain the same as the diameter increases. And also the sample need to be prepared specially to not damage it in the clamps of the tensile machine, the UTM. And so that's why you see this potting sample, as we call them. So steel sleeve with a non-shrink grout to ensure the GFRP bars are well protected. So obviously, as we can see here on the sample after failure at the bottom of the screen, this material is brittle. That's again well known to people who design with ACI 440.11, but you have to imagine when we are moving into the geotechnical world, very often designers are not familiar to that. The exposure to composite material in those ground engineering application is much less than what we could see with RC structure. And so a lot of the education work that could have been done again from ACI 440 committee has to be addressed and copied and transferred to geotechnical work. So again, nothing fundamentally new here when it comes to performance. We have the same observation as we have with a rebar. So we always have to highlight that the performance of a GFRP bar is very different when it comes to the values, the characteristic value. But more than that, as we know from these graphs, it's the whole behavior that is different. So FRP, as we know, is brittle material, means there's only elastic phase in a stress strain curve. That's why we have this red line here, characteristic of the FRP ball. So no yield point, no ductility, and therefore, while the modulus of elasticity is 4 times lower than steel, the elongation at ultimate is much lower. So this is something we always have to remind, because the failure mode and the mechanism engaged in geotechnical application again are different, and that's why we have to address through specific design aspects. Repeat the same way ACI 440 use equation different from ACI 318 for the very same reasons. So this is something, again, a reminder, but extremely important. Those are all the prerequisites before we engage into any geotechnical engineering aspect. So we'll start now with a first area of study. We'll start with those passive anchors, and especially I would like to address the case of soy nail that are mostly used in slope stabilization. And for a long time, we've seen people concerned about designing those products with GFRP material on the basis that the shear of the bar was low. And that's partly due to education that we've been doing on explaining that the material is easy to cut. So this is something really not easy to explain, because people feel we are turning around the properties of GFRP the way we want. What happens when you characterize the shear of FRP bar in a lab through a typical ASTM transverse shear test? You're characterizing the dowel effect, what you see on the left side of the screen. This is the pure transverse shear applied to the FRP bar alone. So it's a very theoretical and pure, again, shear test. In reality, when you install the system in the ground, again, so that can be in rock, that can be in soil, before the system fails in shear, there will be crushing of the surrounding material. That could be grout, that could be the ground itself, so soil and rock. All this material will be compressed, and once its compressive strength is exceeded, will be crushed up to a stage where the actual bar will fail in shear. And that's really important to highlight, because through this deformation, we realized that GFRP was behaving in a very different way than anticipated when characterizing the bolt in the lab. Let me illustrate that a little bit further. So here, what you see on the screen now is a comparative test. So on the left, you have a GFRP bar, which is a fully threaded bar actually, used often as a rock bolt. Of course, on the right side, you'll be familiar with a steel rebar, but I think I can assume many of you have not necessarily seen the test you see on the right. Actually, we've used the ASTM standard that is normally for GFRP bar, and we apply that to a steel bar. Why is that? Actually, most of the time, we don't need to test shear of steel bar. We just know that. We use von Mises ratio, and then we derivate it from its tensile properties. However, we felt it was necessary to compare apple to apple to perform the same test on the same product. So you will see that when you test FRP bar compared to steel in this condition, we get fundamentally different results because there's no surrounding material. Again, this is the pure Dowell effect. However, there's a very interesting BS standard, 7861, as you can see here on screen, that is originally meant for coal mines. So this is a pure geotechnical engineering design guide. And what's very interesting, and they do address the specificities of both steel and FRP. So that's one of the few exceptions I was mentioning earlier, because geotechnical engineering generally only considers steel. This is the test of a simulated borehole. So the sample is tested with its surrounding material. So it can be cement grout, it can be resin grout, but we don't test the bar alone. We do test with surrounding material. And we've run the same test, again, with a GFRP bar and of course with the steel bar as well as a reference point. So let me present it in this way. What's very interesting with the results is on the second column in the middle, bar alone, you can see that a GFRP bar would only develop about a third of the steel bar when tested for pure shear, so the Dowell effect, which is consistent with the perception that GFRP is weak in shear, and also it's easy to be consumed by excavation equipment, tunnel boring machine. However, when you test it as a system with the surrounding material, the performance of steel increases marginally. You see from 416 MPa to 488 MPa, but the performance of the GFRP bar more than double. And for this reason, the GFRP bar would develop 75% of what you get from a steel bar. So what this table is telling us is a non-metallic system behaving in shear can develop actually way more than we suspected, actually a lot, 75% of what the steel system performs. And even more interestingly, the value of 350 MPa is actually what you get from von Mises ratio. So actually, in this case, the GFRP bar develop more than what you would assume for a steel system. So it would actually offer you all the safety you would expect in your design. To explain a bit about that, I invite you to study a very interesting paper from Dr. Thomas, who published it at the World Tunneling Conference. I won't have the time to explain all in details here, but the idea is the reason GFRP can have such behavior is because of the tensile properties. So when you get this deformation, some of the stress will be taken in the tensile properties, and some will be in the frictional. And so GFRP being so strong in tensile, you really get this contribution when you have the system working shear, and that give you, with the model developed by Dr. Thomas, 350 MPa at 90 degrees, which is what we observed. What's interesting is if you were to do that at a different angle, like often we see in geotechnical work, actually GFRP would exceed the performance of steel, and that allows us even to get better behavior. So with all these results in hand, we were able to offer very interesting ground engineering application, starting with soil. So what you see now on screen is an example of non-metallic or partially non-metallic soil. So it's a hybrid system. The reason this is a hybrid system is we did retain splicing system made of steel and even the head made of steel due to mechanical continuity. So the concern with the soil is generally we are way over 12 meter or 40 feet, which are generally typical lengths for shipping, especially for containerized goods. And in order to have mechanical continuity, you need to splice that. Unlike in a concrete structure, we cannot use lap splice because we cannot rely on the integrity of the concrete. Here we have grout that will very often be damaged, cracked through the normal movement of the soil or the ground. So we have to use mechanical system, and so we use a steel coupling system actually made of two sleeves that are switched, so they are mechanically bonded to the bar. It's not actually crimping, it's even more sophisticated. The swedging is extruded sleeve, and thanks to that we can develop 80 to 85% of the bar performance, and having the same in the head location. So repeat, the reason we use hybrid and not just a non-metallic system is to ensure continuity over long lengths, and also in the head location to do pull-out tests. As we know, those systems are extremely light. I mentioned that in introduction, a quarter of the weight of steel means you can easily carry those nails by one man. You see it even carry two nails like here on this example. And to work on complex terrain like slopes, it makes it much easier. So as I highlighted, the mechanical continuity is key. And again, here I wanted to highlight with a practical example of pull-out tests, which are very common on a job. So you would normally test 5 sets, for example, at the beginning of the job, and then there will be an agreement with the consultant and the owner on the frequency of tests. So typical frequency would be 2% of the nails installed will be tested for pull-out. And that's why you need a head that allows you to perform that in situ test. So we are using such system, steel connectors, to extend the bar, to also test in the head location, and that's really give you the best of the two worlds with FRP material that is again resistant to corrosion, that is easy to consume, easy to cut, with the steel system that can develop high strengths in a matrix, in a stud, in a fine pitch thread. Maybe the challenge, however, when you have steel components is cuttability. So those components are small enough to be still consumed by the excavation equipment. So most of the time, statistically, you're going to hit the GFRP bar. But if you were to hit the steel components, it would be very easy to evacuate it like you have a boulder, an inclusion into the ground. And for corrosion, how we address that? We address that the same way we would address corrosion protection of couplers when you have a steel anchor, like a DCP anchor, for example, corrosion protected anchor. We're using heat shrink sleeve that are also used, for example, on steel couplers, steel splicing system for steel rebar, epoxy coated, for example. So the heat shrink sleeve is the best way to protect from corrosion those localized steel components you get in the system. So through all this, we have enough technical background on the tensile, bond, and even shear properties. Also enough answer from the system through steel splicing system and corrosion protection to design a GFRP soil nail. And maybe just to mention one example, this picture you see is one of the big metro station that was built about 10 years ago in Hong Kong. What was interesting is this station was built with a cut slope, and all the slopes you see on this site were reinforced with GFRP soil nail, simply because it was important to not obstruct piling work that would be done at later stage. Hong Kong is a very highly dense area, and of course, real estate promotion surrounding the metro station is the main way of financing those jobs. So the concern of the MTR company was to ensure there would be no obstacle to piling work, and therefore they didn't allow to leave any steel in the ground. So this is typical example of soil nail project, but maybe for the records, as I mentioned, this is over 10 years now. And actually every year Dextra is probably supplying 3 or 4 jobs specifically with this kind of application. So non-metallic soil nails, temporary, and more recently, we are now doing pilot jobs with the Hong Kong Polytechnic University, the local government, to characterize using those soil nail in permanent application on slope stabilization, which is a very big concern in Hong Kong with a high rain season. And so it's very important to stabilize those slopes in Hong Kong. So they are now exploring and through 2 pilot projects using soil nail permanently. Allow me now to move up with new technical concepts so we can address, let's say, somehow more challenging application. After doing those passive soil nail, let's move up to doing tieback, so active anchor. And to move from a soil nail to a tieback, as I explained, we are dealing with a post-tensioned system, and it's extremely important to characterize the creep and especially the creep rupture of the material. So again, not reinventing the wheel. Answers as often are available to us in ACI and ASTM. So we are following the creep rupture test from ACI 440.3 to obtain the million hour retention. So for those of you not familiar, we apply many different levels of stress, purposely very high, to induce rupture and to measure the time, to know when the rupture will occur. What is interesting is those rupture, they occur in logarithmic fashion. So this graph you see at the bottom, the scale is the time, but in a logarithmic scale. So typically number 3 means 1,000 hours, number 4 means 10,000 hours, and so on, up to 10 to the power of 6, which is million hour. And why designer love million hour retention? That give you 114 years of design. So as we can see, the numbers are highly correlated. We see the R2 factor is almost 0.98. So it shows that there is correlation between the stress level and the time, and therefore we could conclude on the million hour retention of that particular GFRP material. This gives us a key factor to design those anchors, but again, in the same spirit of what ACI, I'm thinking, for example, of ACI 440.4 that is used for pre-stressed concrete member. We are not using GFRP for permanent application, so we will only actually address temporary application. Otherwise, creep could become redibitory for GFRP, for glass fiber reinforced polymer anchors. So now, how to achieve that? Now that we've seen the theory with the creep rupture, how to design and obtain tieback, so post-tension anchor. Dextra answer to that is a product that behaves in a very similar fashion to those steel strand or multi-strand anchors. So the idea was to develop again a hybrid system using a GFRP bar on one side and a steel strand on the other side, with the same splicing system introduced earlier, so steel connector. And the idea is to have the same capacity per strand. So when you have a 0.6 inch steel strand, or T15 in metric, we get the same capacity, which is 250 kilonewton. And even in terms of design, we get very similar design value for temporary application, which is 150 kilonewton per strand. So the beauty of this product is ability to design the product the same way. So we end up having the same number of tendons, and it can be installed and tensioned the same way because the product is using a steel strand for tensioning purpose in the head location. So multi-strand anchor are very easy because you can design for a large number of capacity, loads, just by adding more tendons. This system can be spliced, so you can address many different lengths. And as often, the free length is obtained by placing a bond breaker. So we debond the free length, and therefore we can have a fully grotted system just by protecting the GFRP bar from the outside. The bar is free to move inside the free length through this bond breaker, and therefore it's very easy to create those multi-strand active anchors. So as I highlighted, now you can see the product, let's say, without the bond breaker, which is a little bit easier to understand. But the beauty again of the system, again hybrid, everything you see in GFRP will be installed in the ground, and the steel strand, the upper side on the left side of the screen, will be the part you have inside the retaining structure, protruding outside to install hydraulic jack and be able to perform testing. So the idea of a product like this is to be used, I would say, either inside excavation of typical underground car park as an alternative to strutting, internal bracing. So the idea is, yes, I want to be able to install an anchor, and at the same time, I don't want to create issue for the neighboring plots, because you will encroach that into adjacent plots. So instead of installing steel and trying to remove it, we're installing GFRP and know that this GFRP is not creating obstruction. Another application, which is a bit niche, but it's also interesting, is the ability to place this anchor in a location where we know it's going to be destroyed, and typically that's the application of soft ties. So I'm going to introduce you a very short video just to illustrate how anchors have been used in the soft tie location. So it means in the alignment of the TBM, and this helps somehow as a mock-up to prove how cuttable the anchor could be. And further to that, it was able to be used in other location, so pretty much in the whole perimeter of the station. So what I'll do is I'll present the video, and I'll tell you a little bit more right after. So the project I'm going to show you is a project in Doha, in Qatar, and those anchors have been used in many metro stations. So here you have just example of excavation that were done there, and you see the numbers. So on one job site you could see several hundreds anchors. Most of them were relatively low capacity, 3 or 4 tendon, but we've done anchors with 12 tendon. There were 7 layers of anchors in that station, which was crossing of two metro lines, so 35 meter deep, about 100 feet. And so that makes it extremely challenging. So quite interesting project. So let me show you now the video, and then I'll illustrate it a little bit after. So as I highlighted, this video shows to untrained eye, let's say, a typical soft eye breakthrough. So TBM has been able, the tunnel boring machine has been able to bore through the diaphragm wall. But what was really interesting is those anchors installed inside the soft eye area were non-metallic. Actually, maybe you saw this, it was mentioned, it was even carbon fiber, it was CFRP used in that project. And so that really proved that it's possible to design anchors, again, going beyond the original plot or the original print of the excavation, and yet making them of a material that would be easily consumed. So here by TBM, but you can imagine the same thing from the surface, could be a piling rig, or also from excavator in case of open cut, for example, excavation. So after reviewing those active anchor and so post-tensioning, somehow this presentation wouldn't be complete without addressing permanent application. So we've seen those passive soil nail, we've seen those active tiebacks, yet we are doing more and more geotechnical application with permanent solution. So remember, over 2 years, but actually I'm really referring here not just to 3, 5, 10 years or semi-temporary or semi-permanent, as some might say. No, we are designing project with 50, 100 or 120 years application. And of course, that's because we know already very well that GFRP is resistant to corrosion, or actually there is no corrosion as such with GFRP. The concept of having rust or the material physically changing doesn't exist. There's no change of mass, no change of weight. However, as it's well documented, GFRP will be affected by high pH, and so the same way when you have moist concrete, you have a high pH, and this alkalinity will reduce the bar performance. The vast majority of geotechnical anchors are, of course, using cement grout. And for this reason, we are facing the same condition. So again, using all the groundwork, if I may say, of ACI and STM, we use those characterization to say, look, we know in advance the behavior of those FRP material. We can predict by how much it's gonna lose over time. It's minimal and it's very much predictable. It's limited, unlike steel. Once corrosion starts, it will accelerate. So we are using all this work. So we've done a lot of characterization of the material. Again, for those of you not familiar, this accelerated aging test is pretty straightforward. The idea is to conduct tensile tests as per D7205, as I showed earlier, but after conditioning bar. So you get some test bars at T0, at 0 hour, but then you also want to have bars in an environment that is high temperature, so 60 degree, very high pH, and that will give you a simulation of the long-term behavior of the material. So here, example, there are so many different tests performed with large variation in the duration. Also, whether you use moist concrete or you use a water solution, but alkali solution. Also, if you apply stress at the same time or not. But in general, again, best is to refer to ACI for the guidance. The requirement in STM D7957 is to be over 80% after 90 days. And so this is again showing that the behavior of the material is highly predictable. And so we can just apply a factor. So again, in ACI for 0.11, the factor today is 0.85. So we discount the tensile performance by 15%, and then we get the performance of the material over time. And that's really useful, using this for designing GFRP bolts, for example, because the alternative to that would be a steel bolt on which you have to put many corrosion mitigation, so typically galvanization and or epoxy coating and or a corrugated pipe, all this to delay the corrosion, but always with a risk this corrosion happens. So how to do those applications? We have or available to the people designing tunnels, caverns. There's a large variety of rock bolt available. Typically, there are even some self-drilling rock bolt available, but I'm going to address here maybe some of the most common type, which are solid and hollow rock bolts. There is good to have both options available for different type of installations. So typically, hollow bolts are for sure used more to inject the grout once the bolt is installed. Solid bolts are generally installed either in a pre-grouted hole or with resin cartridges, typically in mines. And as you can see, we are using a fully threaded bar, which makes it very easy to add accessories. So here you see we have a non-metallic system. Most of the rock bolts, or almost the entirety of rock bolts, are less than 12 meter, so we don't really have the concern of splicing. However, we still developed special accessories to be able to perform the pull-out test by mobilizing around 150 to 180 millimeter in the head location and be able to develop a large performance in the head location, again, for pull-out testing, as I highlighted earlier. So again, unlike a soil nail, here we are able to use shorter system, and therefore we can rely on being 100% non-metallic. And there are many different accessories available in the head location. So when it comes to having what we would call an articulated plate and nut, so dome plate and nut, or maybe a flat plate and nut. So this is available to the designer depending on the performance and the degree of liberty that is expected. One of the key advantage, again, working underground, especially when you work on a platform, when you work on a bench, is that material being light. It was proven, so this is a very interesting study from Scandinavia, that installing those FRP non-metallic rock bolts is so much easier. Maybe to give you one rule of thumb, GFRP being stronger and at the same time lighter, we can normally cut the weight of the bolt by a factor of 5 to 6. And a typical diameter 32 rock bolt that could be 40, 50 kg when it comes to long lengths, 6, 8 meter, you get it in below 10 meter in most of the times when it's GFRP, through reduction of the diameter and through lower density. So definitely a very big advantage here when it comes to installation. It reduces the risk of incidents or accidents, and of course increase the productivity. So let me illustrate this with some very interesting project. I'm going to use for this presentation a project that is completed and already actually operating in Vietnam, that is storing LPG for an industrial application. So the storage of propane and butane is actually under the factory that is producing synthetic textile, so PP fiber, polypropylene fiber. And the concept is to create a large cavern to store that. This cavern is saturated with water to ensure the gas is trapped and doesn't leak through all the vein, all the joints. And so that makes it very interesting. So let me illustrate. This is an example of access tunnel, and all the white spots you see here on the lining are actually GFRP rock bolts. You can see that it's an unlined tunnel. The same way the cavern is also an unlined cavern. And those bolts are here permanent. So there is the lining you see here is a very short layer of shotcrete that is only here to keep in place very small, let's say, piece of rock that could fall. But all the pinning of the wedges in this underground structure is done by using GFRP rock bolts that are designed to last 50 or 100 years, depending on the application. So you can see how light and also flexible the rock bolt can be, so makes it very easy to install. This is typical geometry of the actual cavern, so you see quite large, 22-meter high, 17-meter wide. They have two bench to produce that anchor, that structure. On a job like this one, over 30,000 rock bolt have been used. But to give you some ideas, we've also supplied some much larger caverns that used in excess of 600,000 rock bolts. Every single rock bolt is GFRP because it has to be resistant to corrosion and designed to last. And currently we are even executing a tunnel project, and rock bolts are also used in similar fashion as permanent rock bolts in this single shell lining tunnel. So to conclude on this presentation, the objective today was to share with you some key parameters. I hope this is clear for you. So we've been through the tensile and the bonding. We've been through shear performance. We've been through creep resistance. And of course, we've been also through alkali performance to address permanent application. Just as a summary, I won't go through the whole slide, but I wanted to highlight or illustrate here example of application that can be done to do a passive or an active anchor, a temporary or permanent anchor. And maybe just to finish on that, I highlighted that we normally use only GFRP for temporary active anchor because we have the combination of alkali requirement and creep behavior. So that's why the most challenging application in geotechnical engineering would be an active permanent anchor. And today, our answer to the industry, and I know this is a consensus with other designers, manufacturers, supplier, is to use carbon fiber, CFRP, when designing permanent active anchor, because the requirement, again, in terms of corrosion, alkali resistance, combined to the creep resistance, make it challenging. And to be on the safe side as far as application addressed, we're using carbon fiber for such application. For the rest, for the other boxes you see here today, we are able to do permanent passive anchor, temporary passive anchor, and temporary active anchor, all with GFRP material. And I'm very happy after that to take question from the room if there is any.
Yeah, Pierre, thank you so much for your outstanding presentation and for graciously sharing your extensive knowledge and diverse applications and perspectives. And I would also like to mention to the attendees that our speaker is he's presenting from Thailand. So again, thank you for accommodating this because it's 11 hours difference. So thank you so much for that.
It's my pleasure.
Let's move to our question answers. So our first question is, what are field quality control, test, inspection required to ensure GFRP is installed correctly or for full utilization of GFRP strength?
Okay, thank you very much for the question at large, and thanks for asking this first question. So I'll give you again first answer that I used again as a red line throughout this presentation is we always start by looking at what's available within ACI and ASTM. So if you look at the specificity of our material, when we do typically a soil nail, the first thing would be Mr. Contractor, recommendation of installation, also inspection. Let's refer to ACI 440.5, for example, that gives all the recommendation for placing, etc. Also, when it comes to testing of the material, we would also look at table 2 of ASTM D7957. There are certain number of tests that needs to be performed on the actual batch that is delivered. So what's specific now to geotechnical application are generally pull-out tests, as I illustrated earlier. So what we offer when we supply the bolt, we also have to work together with the contractor to deliver them the right set of pull-out accessories. So there are a set of couplers, extension bars that needs to be mounted with what we call a stressing chair. And I want to say that actually geotechnical anchors are not forgiving compared to a rebar. If you place a rebar into the concrete, you cast that concrete, who's going to know whether it was done correctly or not, how it's going to perform? You don't really have ways. With those geotechnical anchor, because we do random tests, I mentioned 2% inspection for pull-out test, even with an active anchor, every single anchor is stressed as a routine test because it's part of the way to activate it, to tension it. So actually, in a way, it's much less forgiving, I insist. So all those in situ pull-out tests means you don't just test the batch in a lab and then ship it to site. You have a way to test each product installed at site. If you need more information about that, feel free to contact me. I'm happy to, of course, share with you some specifics on the pull-out test, for example, done at site.
So similarly, like as you answer the question for the quality control, we have another question on the similar thing, but it's on maintenance. So what ongoing maintenance or inspection procedures are necessary to ensure the continued performance of the FRP anchoring systems?
So again, I think the share, again, as you can understand, sharing a lot of the properties with other FRP material and starting with rebar, the whole idea of moving to a non-metallic anchor is to balance the capex and the opex. So we see that initial investment cost might be marginally higher than a steel member. However, the whole idea is to get the OPEX, so the maintenance, close to zero. And to my knowledge, with GFRP bolts, providing design has been done as I illustrated today, we are exactly there. So normally there's no maintenance to be done simply because the bolt will not corrode. The bonding with concrete with cement is excellent. And even if you didn't have full encapsulation, again, you don't have this risk of having corrosion induced. So the beauty again of having a system that allows you to do pull-out test is you can come back after 1 year, 2 years, 3 years, 5 years, 10 years and pull on those bolts. You don't have to do a coring of the concrete to check how the GFRP bar behave inside the deck of the bridge. No, you have those anchors accessible and you'll be able to do that. So I repeat, it's not really maintenance, but there are ways to do simpler observation to ensure the material is still performing. As far as maintenance is concerned, I repeat, it's zero.
Okay, great. Our next question is, has there been any research and testing on pre-peg carbon fiber wraps in place for steel in sleeve splicing for GFRP bars in soil nail application?
There might be. I don't know the full extent of those research. So to my knowledge, I haven't seen anyone being able to achieve a splice with this retention we get today with the steel system. So 80-85%. That's, I would say, we guarantee 80 and we normally reach 85%. So nowhere close without using a steel sleeve. So I like the idea. Thanks for asking and even proposing using carbon fiber. That would be interesting. But maybe to illustrate the challenge, I can imagine that a carbon fiber pre-preg sheet could give enough confinement to not explode, let's say, with the stress. But what we are doing today with the steel sleeve is we extrude it onto the bar, and so it creates actually stress and tension onto the bar. So we are able to deform that steel sleeve to transfer the load, and I'm not aware how we could achieve that with carbon fiber. So somehow this is maybe a frustration that we don't have a non-metallic system, but it's good news. It means we still have a lot of work for the years to come to develop that. So again, thanks for offering this idea. That's worth investigating.
Yeah, Thank you. So is the alkali resistance dependent on the diameter of the GFRP?
Excellent question. I was reviewing some papers actually today around that question, and um, I would say in general it's seen that uh, alkali resistant will be better on larger diameter, so it would go against the tensile behavior. It is true that if you test a small diameter, 6, 9, 12 millimeter, or the small number of bars in US system, generally the alkali resistance will be lower. It's simple due to the ratio between the surface area, the section, and so in between the surface area, the perimeter, and the section of the bar. So yes, bigger bar have better performance. This being said, if you have the right raw material and process, and the two are necessary, then you are able to meet the requirement of AACI and ASTM, so typically higher than 80% retention, even with the smaller diameter.
Yeah, got it. So our last question is, what is the expected service life and durability of FRP anchoring systems, particularly in different environmental conditions?
So I would say, as far as the alkali resistance is concerned, so I'm putting aside the effect of the stress. I put aside the creep and post-tensioning. Again, when it comes to alkali resistance alone, I would say the approach is really the same as what we see in ACI 440.11, rebar in concrete. We're able to, by applying a factor of 0.85, so discounting by 15%, address those permanent application. Even more, why we can do that is we've been running the same tests, same protocol in seawater, so water with chlorides, to simulate again the salt you will have present in water. And so whether you are in a pure concrete environment, alkali, or in seawater, or combination of the two, the retention remains consistent with this 85% retention. And also, I've seen, again, a lot of papers explaining that all those accelerated aging in this water solution, alkali solution, are way more severe than what you get in reality. So again, once you apply this factor recommended in ACI for 0.11, the 0.85, you definitely capture for what it will be environmentally. And again, the only thing on top of that are provision for creep. So as I explained, the million hour retention is 54%. So if you do have an application where there's constant sustained load, you definitely have to apply an additional provision, so typically a factor of 2 at least, to cater for creep rupture.
Yeah, great. So thank you again for answering all the questions. This ends our question and answer session. I have few more slides before we end our today's session. Um, so this is the list of upcoming webinars at ACI University. Please visit our aciuniversity.com to register. And this is our so join us at the ACI Fall Convention in Boston for an insightful workshop on FRP composites in the face of fire, organized by NEX and featuring expert speakers. For registration and additional details, visit the convention page on the ACI website. And additionally to this, we again have another session on nanopolymer composites organized in conjunction with ACI 241 committee, featuring expert speakers who are the pioneers in the field of nanotechnology. So don't miss on this opportunity to enhance your knowledge in this field. All the information is available at on ACI website. You can visit ACI convention page. So thank you again for the speaker. And last but not least, thank you for all the participants today for joining the webinar. We look forward to having you with us again in our next webinar. Thank you so much.
Thank you, everyone.